All right. So today we have first derivatives and graphs. So what we're going to do today is um, graph functions based on the characteristics of the first derivative. So the first derivative tells us a lot. The first derivative tells us the slope of the original function, which means it could tell us if the original function is increasing or decreasing. And that can tell us whether we have maximums or minimums. And the way to do that is by finding something called critical points. And of course, I'll get into all of that because the first 2 pages are nothing but definition. So theorem 1, increasing and decreasing functions. So for number 1, this says if the first derivative is positive on some interval AB, then the original function will increase and the graph will rise from left to right. So remember that derivative just means slope. Derivative is fancy for slope. So if a derivative is positive, this means there's a positive slope, which means a function is increasing. And this is all stated in the chart below. So we say if the first derivative is positive, the original function increases and the graph will rise. So examples of increasing graphs would look something like this, up and to the right, or curve up and over. Those are all examples of increasing graphs. Okay. And then the second part says if the derivative is negative, then this means that the original function would decrease and the graph would fall from left to right, as stated in the chart as well. So again, if the derivative is negative, then the original function decreases and the graph will fall. So examples of a falling graph, basically take this box and flip it over. So you'll have a graph that falls down to the right, curves down to the right, or curves under and to the right. So these would be examples of a decreasing graph. Okay. So now, based on a graph increasing and decreasing, we can find things called local extrema, or maximums and minimums, local maximums and minimums. Extrema is just a fancy word to describe them. So number 1, when the graph of a continuous function changes from rising to falling, a high point or a local maximum occurs. So the graph down below would represent a function rising and falling. So if we look at the first graph, this graph would be rising and then falling. And if you rise and fall, then you create a local high point called a local maximum. Okay, that's number 1. Number 2 says when the graph of a function changes from falling to rising, a low point or a local minimum occurs. And that's going to be pictured, of course, on the second graph. So if our graph goes from falling to rising or decreasing to increasing, a local low point or a local minimum is created. Okay. And then 3, the value f of c is called a local extremum if it is either a local maximum or a local minimum. So what's going to happen is that this value of c is going to be called a critical number or a partition number. So the way we find c is by finding the first derivative and setting it equal to 0. So all we really have to know to summarize it is that maximums and minimums will occur at these critical numbers. And yes, I'll describe more. Like I said, we have another page of definition. But in 3a, it says a point on a graph where a local extremum occurs is called a turning point. So the reason that these local maxes and mins are called turning points is because the graph changes direction. So on the first graph, we went from increasing to decreasing. You increase and you decrease. So at that maximum, the graph changes direction. On the second graph, we went from decrease to increase. And we see that the graph again changes direction. So these are called turning points as well. Okay. All right. So that covers increasing and decreasing of functions. And don't worry, we're going to get more into it. But any questions on this first page? All right. You're like, what is he talking about? Okay. So the next page, like I said, more definition, we get into critical numbers. And a critical number is a number that we find from the first derivative. So the definition says that a real number x in the domain of f such that the derivative equals 0 or the derivative does not exist is called a critical number of f. So this is telling us that to solve for a critical number, you'll take the derivative, you'll set it equal to 0, and you'll solve for x. Critical numbers of f belong to the domain of f and are partition numbers for the derivative. So what that means is that once we find critical numbers, we're going to create a sign chart, a number line, and plot those critical numbers on it, which means they break up the number line, hence being partition numbers. I guess I could draw a little graph of that. Let's see. Here would be a number line. And let's just say I have a critical number somewhere here. So that would be a partition number because it breaks up the number line. Okay. It says the derivative may have partition numbers that do not belong to the domain of f, so they are not critical numbers of the original function. All that says is something we don't have to worry about in this class because we're not going to get anything that crazy. But again, you can find critical numbers that belong to the derivative but can't exist in the original function. So that's a possibility, but again, not for this class. We don't get crazy like that. And then the third one says, at a critical number, x equals c, where c is any real number, a horizontal tangent will exist. So what that means is that at a local minimum or a local maximum, you will always have a horizontal tangent line. And I can draw a little graph of that. Let's say, oops, here's my graph. And let's just say I have a local minimum and a local maximum. Okay. Oh, there you go, catch up. Okay, so at this local maximum and local minimum, for my critical numbers of C, we say a horizontal tangent line will exist. So this means that you would have a tangent line that shares this point that is horizontal. And same thing down here. And this only makes sense because when you find critical numbers, you set the derivative equal to 0, which means you are setting the slope equal to 0. And the only types of lines that have a slope of 0 are horizontal lines. So whenever you find critical numbers, you're also finding where horizontal tangent lines exist. Okay, that's critical numbers. So I like to keep everything simple. To find a critical number, just take the first derivative, set it equal to 0, and solve for x. Okay. All right. And now the next theorem, local extrema and critical numbers. So now we see how critical numbers and maximums and minimums work together. So we come across something called, actually, let me read theorem 2. So it says, if f of c is a local extremum of the function, then c is a critical number of f, which means that if a max or minimum actually exists, then our critical number is a critical number of f. To find local extrema, we must find all critical numbers of f and test each one to see if it produces a max or min. So what that means is, again, we're going to create a sign chart. We're going to plot our critical numbers. We're going to pick test points, and that's going to tell us where we increase or decrease, which brings us to the first derivative test. Let C be a critical number of f. Construct a sign chart for the derivative close to and on either side of the critical number C. All right. So number 1 states the existence of a local minimum. This means that if your sign chart decreases and increases, meaning if your sign chart goes from negative to positive or decreases and increases, then this verifies that this critical number of C will be a local minimum. Okay. 2, we have a local maximum if your sign chart goes from increasing to decreasing. This means that critical number will be a local max. And we saw that on the first page. It makes sense because if we go back here, if you increase and decrease, you have a local max. If you decrease and increase, you have a local min. Okay. And then let's say that your sign chart doesn't change signs. Let's say that your graph goes from increase to increase. This means that you will have no max or minimums, no extremums. And if your graph decreases and decreases, this means, again, you will not have any local extremums. All right. So again, what we're going to do today is we're going to be given a function. We're going to find the derivative of that function. We're going to find the critical numbers. We're going to create a sign chart. We're going to pick test numbers. And then we're going to use all that information to sketch the original function, which is what we have coming up next. Just had to get through all that lovely definition. Okay. Number 1, find intervals on which a function is increasing, decreasing, and the local extrema. Okay. So we are given the function x cubed minus 6x squared plus 9x plus 1. We want to know what intervals are we increasing on and what intervals are we decreasing on. So again, in order to do that, our first step is to find the derivative. How much more can I zoom in? Right there. Perfect. Okay. So given that function, our first step, I'll put it under A, is let's find the derivative. So f prime of x is going to be 3x squared minus 12x plus 9. That's our first step. Find the derivative. And then take the derivative and set it equal to 0, which means we get 3x squared minus 12x plus 9 equal to 0. And now we solve for x. What could I divide out of all 3 of these terms? Or I guess, what could I factor? Out of 3, 12, and 9, I could take out
a 3.
A 3, right? I could take out a 3. But since it's an equation, I'm not going to factor it out. I'm just going to divide it off. And we're only allowed to do this because it's an equation. So this means I'd get x squared minus 4x plus 3 equal to 0. And now all we have to do to solve this equation for x is factor it. So you have minus plus. That means I'll have x minus a number, x minus a number. And these are the easy ones to factor because all you have to know is the factors of 3. What are the only factors of 3?
1 and 3.
1 and 3. There you go. And now if you solve for x, you'll get x equals 1 and x equals 3. And these are now called my critical or partition numbers, which means the next thing we're going to do is plot them on a sign chart. Any questions so far? Let's see, B. So here, create your sign chart. It goes from -infinity to infinity. And we're going to put our critical numbers on it, our partition numbers. 1 and 3. Okay, I'm going to zoom in. And what we're going to do first is create intervals, the intervals that are broken up by the partition numbers. Intervals. Okay, so my first interval is -infinity to 1. My second interval is 1 to 3. And my third interval is 3 to infinity. So these are the intervals we are going to now pick test numbers in. So that's our next one. Test numbers. All right. So from the first interval, -infinity to 1, somebody give me a test number in between there.
0.
0. Good. And then from 1 to 3, somebody give me a number between there.
Dos.
Those. And from 3 to infinity, we can pick
4.
4. Okay. So here's an important part. This is a sign chart for the first derivative. So you need to take these x values and plug them into the first derivative. So this means you'd have f prime of 0, f prime of 2, and f prime of 4. Okay. And now let's look at our first derivative again. And I'm going to use Desmos. Desmos for the win here. Wherever you are. There you go. Okay. So what I'm going to do is type in my derivative first. 3x squared minus 12x plus 9. And then I'm going to use that table feature that Desmos has. And I'm going to type in the test numbers that we wrote over here. So back over here, 0. Whoops, didn't mean to do that. That should be x. There we go. Up there. 0, 2, 4. Okay. So this means at 0, we get a positive 9. So I'm going to put the sign there for a reason. We get a positive 9. At 2, we get a -3. And at 4, we get a positive 9. Okay. So the reason I'm putting those signs there is it's going to tell us on our sign chart what intervals we are increasing on and decreasing on. So we really don't care about the numbers. We only care about the sign of the number, whether it's positive or negative. Okay, now back to the notes. So what we're saying is that when we picked a test number of 0, that was in between -infinity and 1, we saw that no matter what number you pick, you're always going to get a positive outcome. So this means that from -infinity to 1, the function is increasing. And then when we picked a number between 1 and 3, we saw that the output was negative, which means no matter what number you pick between 1 and 3, the outcome's always negative. So you will be decreasing. And then last, we picked 4, which is a number between 3 and infinity. And no matter what number you choose between 3 and infinity, the outcome will always be positive, which means we are always increasing. Which means, since we have our intervals of increase and decrease, we can answer the final question. What intervals do we increase on? And what intervals do we decrease on? So looking at your sign chart, what are my 2 intervals of increase?
-infinity to 1 and 3 to infinity.
There you go. -infinity to 1 and 3 to infinity. That means That leaves my interval of decrease 1 to 3. There we go. That answers the first question. Everybody good with that? All right. Then B, does the function have a maximum or minimum? And if it does, what is the value? So here, all we have to do is reference the sign chart. So if we look at our sign chart above, we see that, look at our first critical number at 1, and look at what your signs are doing. At the critical number of 1, we are increasing and decreasing. This means that at 1, we have a max or a minimum.
No, minimum.
So other way, increase, decrease. Means you have a local max, right? Because if you increase and decrease, you create the local high point. Okay, and then look at 3. You decrease and then you increase. So you would decrease and then increase, which means that 3 is going to be a what?
Minimum.
A minimum. Oy, come on, computer. Is local minimum. Okay, but it's not over yet, because now we want to know what are the exact locations of these maximums and minimums. And to find that, we must plug these into the original function. So be careful with that. So for these, we will say, actually, put it together. Plug into f of x, the original function. Okay, which means that we're going to have f of 1 and f of 3. F of 1 and f of 3. Now, let's go back and look at our original function. And I'm going to type that in Desmos just to make it go faster. There we go. There we go. There we go. And close that. And I'll type in x cubed minus 6x squared plus 9x plus 1, table feature, and 1 and 3. Perfect. So when I plug 1 in, we get 5. When I plug 3 in, we get 1. These are the exact points where you'll have a maximum and minimum. So these are the points 1, 5 and 3, 1. Okay. There we go. I'll leave that like that. Okay. So now, all we want to do now is sketch a graph of the original function. Yes, we see the perfect graph on the left side, but we're going to sketch this graph by plotting the max and minimums and following our sign chart. That's what we're going to do here. So I'm going to plot the points 1, 5 and 3, 1. All right. 1, 5, which is 1, 2, 3, 4, 5 right there. And I'm going to mark that as a 1. And then the next point is 3, 1. 1, 2, 3, there we go. And here's 3. Okay, like I said, let's go ahead and graph it by using the sign chart above. So what we're saying is that from negative infinity to 1, the graph is increasing. So the way that looks is like this. This what it would look like. It's all increasing. And then from 1 to 3, the graph decreases. And we would look like that. And then the last part is from 3 to infinity, the graph again increases. And there you go. So that's how you would sketch the graph by using the maximums, minimums, and the sign chart. Oh, and the last part of this says to add horizontal tangent lines. Well, remember 1 and 3 are my critical numbers. And at these critical numbers, you will have horizontal tangent lines. So this means all you have to do is draw something like that, and that's it. Okay. And that's how you sketch a graph by its first derivative. Any questions? We got this?
Yeah, we do. We got it.
All right. One's got it. We're good with that. All right. Okay. Well, then we'll do one more. Exact same thing, just to get it down. All right. Example 2, same exact thing. Given this function, find the intervals of increase, decrease, max, and minimums, and sketch the graph. So first, we find the derivative. Zoom, zoom, zoom. There we go. All right. So I'll just say tiny step A, f prime of x. We get this derivative. Oh, come on, laptop. Don't be slow today. And you get negative 4x cubed plus 100x. And then you take your derivative and you set it equal to 0. Negative 4x cubed plus 100x equal to 0. And now we solve for x. Well, we can factor here. I have a 4 and a 100. What could I factor out?
The negative 4x.
Good. A negative 4 and an x, you said, because I have an x cubed here and an x there. So I'm going to take out a negative 4x, and that's going to leave me with x squared minus 25 equal to 0. Okay. Can we factor more?
Yes.
Yes. We see that x squared minus 25 is a difference of squares. What will that factor to?
X plus 5 and x minus 5.
There you go. Woohoo. Now, set all 3 terms equal to 0 and solve for x. So you'd have negative 4x equal to 0, x plus 5 equal to 0, x minus 5 equal to 0, and my critical numbers are going to be 0, negative 5, and 5. These are, again, my critical and or partition numbers. Which means we move on to the sign chart. There's negative infinity. There's positive infinity. Plot your critical numbers. -5, 0, and 5. How much room am I working with? I got a lot of room. I'll just move this down. There we go. Okay. And now zoom in. Once again, we'll do the same thing. Intervals. Negative infinity to -5. -5 to 0. 0 to 5. And 5 to infinity. There's my intervals. Next is my test numbers. We're going to have 4 of them. So x equals, x equals, x equals, x equals. Give me a number from negative infinity to -5.
-4.
High or lower, lower. -4 would be in here.
Oh yeah. Oh, -6.
There you go. And then we could choose -4. Why not? 0 to 5. Give me a number.
1.
1. And 5 to infinity.
6.
6. Remember, these get plugged into the first derivative. So you'll have f prime of -6, f prime of -4, f prime of 1. Ooh, forgot my dots there. And oh yeah, f prime of 6. And here's where Desmos comes in. Oh, whoops. Boom, 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 boom. There we go. Oy. My laptop's like, it's the end of the week. I'm done with you, man. I still got one more class to go, laptop. Chill out. All right. So I'm going to type this in. -x to the, the derivative. Whoops. -4x cubed plus 100x. Do my table feature and then scroll back over here and type all these lovely numbers in. -6, -4, 1, and 6. And like I said, we don't care about the number. We only care about the sign. So I get positive 264. Someone's going to say plus. I get -144. I'm going to say minus. And then 96. And then -264. You don't really have to care about the numbers, just the sign. Okay. And then, with that being said, we know how to fill out the rest of the sign chart. Positive means we increase. Negative means we decrease. Positive means we increase. And negative means we decrease. Which means we can answer what it's asking us. Don't flip out on me, laptop. There we go. Where are my intervals of increase and decrease? And increase from the sign chart is -infinity to -5 and 0 to 5 And decrease would be -5 to 0 and 5 to infinity. There's that. Yee-haw. All right. Like I said, same as last one. Everybody go with that.
Yes, sir.
Which means the next one's really easy because you use the sign chart to find them. So for B, it says, do we have maximums or minimums? So let's look at our first critical number. At -5, we increase and then we decrease. This means that -5 will be a what?
Maximum.
There you go. Local max. And then you look at 0. 0, you decrease and then you increase. This means that 0 will be a
Minimum.
minimum. Which means that 5 will be just like -5, a local
Max.
max. Now remember to plug these into the original function because that's what we are graphing. Plug into f of x. So you have f of -5, f of 0, f of 5. Okay. Desmos, all right, don't freak out. Let's do this. You there, perfect. Where's my original function? Up there, -x to the 4th plus 50 x squared, table feature, and let me just go back down here, and I'll type these in here, -5, 0, 5. So 625, 0, and 625. There we go. Okay. And again, these are actual coordinates. So this is the point, -5, 625, 0, 0, 5, and 625. There's the graph on the left, but again, we want to sketch this by plotting the max and mins and using the sign chart above. All right, the highest Y value is 625. Oh boy. So that means we can just make this by 100s. So this would be 100, 200, 300, 4, 5, and 6. And then there's 0, 1, 2, 3, 4, 5, and 1, 2, 3, 4, -5. Okay. Here I'll plot the points. -5 and 625, somewhere right there. 0, 0, and then 5 and 625. There's my points. And now using the sign chart, from -infinity to -5, we increase. And then from -5 to 0, we decrease. And then from 0 to 5, we increase. And from 5 to infinity, we decrease. And that's how you draw the letter M. Okay, there it is. Again, it's a repetitive process. Take the derivative, set it equal to 0, solve for x. Get critical numbers, plot them on your sign chart, pick test numbers, and then find your intervals of increase and decrease, which will tell you where your maximums and minimums are, which then can help you sketch the graph by just plotting the max and mins and following the sign chart. Any questions on that page?
Negative.
Oh, good then. Last one. So this one, they've already put the work in for us. They're giving us a sign chart. They're showing critical numbers on the sign chart. And they're even giving us an XY chart to plot. So all we have to do is sketch the graph by using the sign chart and the points given. So let's go ahead and do that. Where's my, there it is. So the first point up is -2, -1. So -2, -1. Oh, way
I like
off.
that color.
Right there. It's fun, right? And then the next point is -1, -1. -1, 1 right there. And then the next point is 0, 2 right there. The next point is 1, 3. 1 and 3. And then the last point given is 2, 1, which is right there. All right. So we have all the points given from the XY chart. Now just follow the sign chart to graph this. I guess I should label my X values down below. This is, or just my critical numbers. There's -1 and here's 1. So based on our sign chart, we say that from -infinity to -1, we are increasing right there. And then from -1 to 1, we are increasing again. So it would curve that way. And then from 1 to infinity, we decrease. So we'd curve up and down and ugly, but there you go. And